Ladies and gentlemen, thank you very much for the invitation of coming here and speaking about the project Radar. I think it's going to change a little bit gear compared to what we heard this morning. It's going to scientific and science going from legislation. So I hope in the next 20 minutes I will give you an overview of what the project, thanks to the European Commission, has been able to achieve in the last 4 years. The main target was really to get a platform, and I think we heard this morning very much the fact that if you look at the reach and the classification of the chemical compounds and so on, they are changing with time. So being able to have a platform instead of having just a specific, let's say a specific antibody versus a specific chemical, it makes a lot of sense in the long-term development. So this project was aiming at having a platform that will allow us to go from, let's say, the water to the alarm, or the water to the detection to the wireless communication, so that we can get to an alarm system, or we can populate some databases about the status, possibly real time, of some of the chemical pollutants and toxins in the environment. I'm Stéphane Fournier. I'm from the CSEM, which is the Swiss Center for Microtechnology and Electronic in Neuchâtel. And so I'm also the coordinator of the project, and I'll go a little bit more into the project. So bear with me for a second. First, hoping that this will work. Yes. First, background. I think we also had not only coffee but also water. And I think one thing that is very interesting, especially in Italy, Italy is the third, actually the first European consumer of water in bottle, which is very intriguing. I don't know if it's San Pellegrino that makes it so good, but anyway, the fact is that the bottled water is in average 1,000 times more expensive than tap water. And that's, I think it goes to 2,000, like in some countries, to maybe 300, and depending on the size of the bottle and so on. But it's very important that if you see the price you pay for your bottled water and the price you pay for your tap water. Now the expectation, I think, from you, from me, from everyone, is that the safety, meaning that I guess when you drink bottled water, when you drink tap water, you expect not to be sick from either or. It means that the bottom line is that there's an extreme pressure on the cost of the quality of the tap water, which is the environment, and you don't have actually the means for that. And not having the means but having to guarantee makes, I think, the local governments and the administration, it's like almost impossible to task to start with. And I think this is why we believe, and I think why in the Radar we try to address that, is how can we make a system that actually has no human intervention, that is actually completely monitoring the environment, alarming, without having to have the high price that you cannot afford when you look at environment and water in the environment. This being said, I think I'd like to address 3 topics. One is the requirement for remote surveillance. I think it's the why, the what, the where, and the when. The second one is what is Radar about? And I think I'll go a little bit into the rational design aquatic receptors and how they're integrated in the sensor platform. And the last, but not the least, is really what is the outcome from going from sample to results to alarm. Going to the first, the why. I think we already heard this morning, so I'm glad I don't have to go through the legislation and so on, but I think there was a declaration where it was critically given that we need to have not only, I guess, a prevention, but also a continuous monitoring of the carcinogens, mutagens, and reproductive toxicants in the environment. Which one of them? I think there are many of them, and I think we saw that list. Importantly enough is that one thing is that this continuous detection is something that's important. So moving from maybe a sampling at one time in I guess a month or one time in a year to something that is more continuous is definitely a need. The second question was the what. And I think for Radar, the focus was the EDCs. And I think out of the EDCs, we decided to go on 2 estrogen compounds. We heard that it's not yet on the list, but it's on the watch list. I think we thought that it's a good case scenario for us. Polycyclic aromatic hydrocarbons as being the second one. Out of those, we had to choose model compounds, and we choose the BAP and the E2 as being the 2 model compounds. And so that was really just to show that the platform can be actually very useful for monitoring those in the environment, knowing that we want to be able to modify that platform very minimally in order to be able to get to other compounds. These compounds are very interesting because they go into one of the big problems is the PPT to the PPB. So when we look at water, whether it's in the environment or anywhere else, the levels are of course much smaller than if you were to look at, let's say, a fish or maybe some of the sediments that actually accumulate in some of those compounds. If you look at really in the water, then you're really going to part per trillion, part per billion. So that makes the stress, I think, on three things. One is multiplexing. I think the fact that we could do, we cannot look at only like one, let's say one microarray, one strip that can measure actually only one compound, but we want to have a multiplex compounds. One thing that we need is very interesting is the specificity. And somehow we want to be specific enough, but somehow we also want to be generic enough. And specific enough, why this is important is because you want to somehow know which compound, but you also want to be generic enough that if you have an unknown compound that will be actually affecting, you want to catch that compound before it's too late. And that makes it also very difficult in this. And the sensitivity, we have part per trillion, part per billion. So these are very important criteria. So after the why and the what, we'll go in the where. And we talked about surface and drinking water, food processes. These are the two of the focus that we have. If you look at these two pictures, you see that the environment is very different from one to another. And I think now I'm going really into basic science and basic stuff is sample filtration is actually an issue because you have leaves in a river stream and we put our sensor in some river streams and it gets clogged if you don't prevent that from going to the sensor. It's not so important to measure it, but it's very important to have a system that is actually can be in a water, for example, stream for weeks. Sample pre-concentration, we're just talking about level of in water. So these are two other attributes that we need to look at when we make this system. The last but not the least is the when. I think we put our focus at any time from sample to result, from result to alarm. So if you look at this graphic, what it means is that if you have a river and you will have somewhere a radar module that is sensing, this sensor is actually transmitting wirelessly to a central, I guess, through a wireless system so that you actually get a direct connection between the measurement that is done and the trigger. We already have a lot of those systems in place, but I think important for us is that we also need to be able to remotely control our sensor. It means that from an energy perspective, from a low power and a green emission, maybe not as close as we are doing in this conference, it's very important to be able to turn on and off this sensor. If we use it once a month, then we can have it on sleep mode for 29 days or 28 days or 30 days, depending on the month, and to have it useful, I mean, like measuring for 1 day. So this remotely control is important. The autonomous system, so battery powered or energy harvesting in the future, and the wireless communication. So now if you look at, I put a lot of, let's say, of bullet of things that are very important for this system. So let me now go to how we did it. And in radar, what we started is, we said, okay, we have a sample, water. We have an alarm at the end that we want to trigger. What do we need to do in order to get from A to Z in a system that can be autonomous and out there? So clearly, water sampling is the first point, and I think it was addressed already before. But then sample preparation. It means from getting rid of leaves to getting rid of the larger particle to getting to something that is useful for let's say, for the assay itself. It's important to know that this is usually now done in a lab, so you spend an hour, 2 hours, or 3 hours, and you get from the sample that you have from the water to the sample that you can analyze. We wanted to make it automated on site so that you don't have to go through it. The second one is that you have to be, as I said, multiplex. You have to be able to react. You have to be on which toxin or which pollutants you want to measure. So the biological recognition element is very important, and we spend quite a lot of effort on this biological recognition element. I'll get to it later. The assay, being able to have a cartridge which allows you to do multiple measurement in total, and the detection module. Once you have this, you actually get to some data. Then you want to have a wireless system that allows you to give you an alarm. Now, I think what was very important in the project is to get all of those in one, say one box or one instrument that you could actually place in the field so that you can actually do this measurement on site. We are lucky enough to get a grant on which we had 7 partners, the CSEM that I already mentioned, but we had 2 SMEs. One is Elysium in England, and one is Optics Balzers in Liechtenstein. And then we had the rest were more like the academic partners, the RRB in Ticino, the Joint Research Center in ISPRA was also part of the consortium, and the RICILT. And then we had, in this case, application partners, and I think Elysium, being an SME, was also looking at fisheries, and NIB looking at the seawater, and the RICILT was looking at the food processes. And so we had this application partner to really try to make it improve. So now we remember I had 4 different areas. One was sample preparation, one was the I guess the biological recognition element, one was the sensor, and one was the detection system. Now I just want to give you an overview of what we achieved in the last years of those, knowing that we will have some detailed presentation later, I guess tomorrow, on some of those topics. So one, going on the sample preparation, we really had to design a macro filter. And macro filtration is really getting rid of leaves and other things that are, or rocks that are in the river. To a macro filtration is really going to, let's say, the millimeter to the micrometer, going to the system that was an extraction pre-concentration unit. This unit was actually is a fully autonomous unit. So that means that the sample comes in and you get the pre-concentration. It's based on SPE, extraction, but it's really at the level where it's miniature. So we can go with liters in and we get out like 100 microliters of pre-concentrated and treated sample. I just give you a couple of data. It's fully automated sample preparation was achieved. It's tested for weeks in the Rhine and the Landquart. I don't know if because we are at, let's say, somehow at the beginning of some of these water districts, so maybe we had less problems. So we need to test it in other places as well, outside Switzerland. We got up to 1,000x concentration of the ethinyl estradiol. I think this is important to see that this is achieved in an autonomous system. I'm sure if you do it in the lab and you spend the 4 hours you need, you can also get to it, but maybe not in a very autonomous way. And up to 100% extraction of small toxins. So this system is actually at the point where I think it's very useful for making, I guess, for bringing the sample to the detection. The second, it continues sampling. The second part is the biological recognition element. And here I think I want to go into something that's maybe a little more technical. But most of the people are, of course, today we're using antibodies against some of the toxins and pollutants because they show that they have the highest sensitivity and specificity. And today, I think to date and today, there's nothing that is better, whether it's, I think, different ways of molecular imprinted polymers or aptamers and so on. They didn't get really to it. We looked at a very different approach where we said, okay, if we take a receptor, and a receptor like an estrogen receptor in this case, this receptor is actually going to be able to bind whatever is toxic. So without having to know what this green, orange, or blue little square is, if it's binding, it's something that is problematic. So we don't have to know actually what we want to target, the target molecules, and we will have an alarm system. What it means, however, is that we need to be able to reproduce these estrogen and forest hydrocarbon receptors, put them on a chip, keep them alive, and it's a very different ballgame than doing this with antibodies. And so what we managed to do there is that we really managed to get receptors for both the estrogen and the hydrocarbon. And why from aquatic organism? We thought that because the sensor was in the water and the environment, it will actually be much more native and be, in that case, useful for a longer time. The best ever aryl hydrocarbon receptors was EDCs. And I think once we had I'd say the wild type here, we started doing some mutants. And doing mutants means for us that we really went into in silico model and then to making these mutants, and making some of the changes allowed us to rational design those to increase the specificity, sensitivity, robustness. And for us, what was important is that now we had a way to look at all compounds that will be, let's say, EDCs that will be having interaction with an estrogen receptor. And if we tweak it, this receptor, we can either make it very broad specificity, meaning for a class of compound, or we can make it very targeted to a very specific compound. And that will allow us to really, in that case, mimic what, I mean, not saying that we are going to toxicity, but we're saying we are going from one compound to a class of compounds that are actually of interest. And this is, I think, a very big point about this. I don't want to go much further. I think there is a plenary session tomorrow at 9:40 where there's going to be a talk about specific these receptors. The third was the multiplex assay. I think we had to design our own assay because, again, we are using receptors, and the idea was that we had was we want to make it as a label-free assay, and I'll get to this topic afterwards. That means that it's possible to do a continuous monitoring, and this is not usually provided by the, I guess in ELISA, for example, you have a sandwich immunoassay where you need 2 antibodies, you need some washing steps in between. So there we had to redesign the assay and optimize the assay. I think what we managed to do is multiplexed assay 8 channels in parallel, and you can see them on this chip. We managed to make it stable, stable peptide chips, 150 samples we achieved. Fast assay, 3-minute injection, total 8 minutes per cycle. It might not be useful to be as fast when we do monitoring over long term, but I think it's possible to do it. And a good sensitivity for example, the 18-estradiol. So we are at the level where we are in the ppb or ppt, depending where we are, and I think it's a useful instrument. There was also a session on a talk on that specific assay tomorrow. The last of the 4 points after the sample preparation, the biological recognition element, the chip is the sensor. And there, I think if I put just as a background, like how you will run a fluorescence immunoassay where you have a capture antibody or you have your sample of interest, and then you have a little flag that gives you the color that allows you to measure this. By going to the new system, which is the Argos system, we label-free angle interrogating optical sensors. The goal was that as soon as one of these blue square binds to the green species, you actually see a change in light. And I'm not going to go too far because we also have a talk on that one, but so the bottom line is that you don't need to have this yellow secondary antibody or let's say or the label to detect when there is an interaction. So if you think about the green part being the estrogen receptor or the aryl hydrocarbon receptor, as soon as one toxin or pollutants will actually be attached to it, you can actually detect it. That makes it the system, let's say, we don't need to do washes, we don't need to do any sample treatment or any treatment on the assay side. It's really, it enables it to be continuous. So it's a label-free detector. I think we make it compact, and I think you can see here, after quite a lot of effort, it's in the box, but it's compact, low power, so it can be battery operated, cost efficient. Since we can use the chip over the long term, we don't have to have reagents that we have to use for each assay. It's a fully integrated system. It has the wireless compatibility. We show that it has a very high sensitivity for the field. I think you saw before going to ppb and ppt is possible. And it's rapid, autonomous, and on-site measurement for the wireless communication. So now I think, this being said, I think I just want to conclude on the outcome. We showed that we made a portable, actually we made 3 of those systems, so it's not only one system for one paper, but we have a portable modular remotely connected platform. And again, a platform will allow us to change from one chip to another, from one, let's say if we go from 8 data point to 24 data point, we will be able to really make it modular enough to follow, let's say, a REACH initiative or others. It's remotely controlled, and we can look at different toxins and pollutants in the environment. There are several advancements on their own. I think if you look at the aryl hydrocarbon receptor, first in kind, the pre-concentration unit, the Argos system. So these are other also systems that can be used in other, let's say, other fields than the environmental monitoring. And if I look at, again, maybe these are just all the things that needed to be, all the attributes that needed or specification that are needed for the system to be useful out there. And with this list of things that we have achieved, I would like to close my talk and thank you very much for your attention.
Thanks a lot. With you, we have swapped from normative presentations to quite technical presentations, and I think there will be probably quite a lot of questions now. Yes, you see immediately.
Yes.
Your sensors are protein-based, and I would like to know for how long you have them stable in the on-site when you place them in the liver or in the water.
So I'll give you a two-tier answer. The first is the first time, the first receptor we had, not stable at all, except at minus 20 degrees. I think what happened afterwards, and I think tomorrow maybe we'll address that question a little bit more with Rita, and I think the RRB and the GRC have been putting a lot of effort on doing this in silico mutant generation, and I think you have seen as well here that we managed to increase the stability a lot. I think the question is, are we never going to get to aptamers or something that is, I'll say, completely like chemical? I don't think so, but I think we can at least go into this direction and make big progress.
Because for a moment, it doesn't last long enough to be used for long-term monitoring.
I think we also have different ways of doing this. If you want, what we said is that we can use it for like 29 days on sleep mode and 1 day on working mode, so that allows us to actually have sensors that can last for longer. As long it's not always that it's in contact with water all the time, and so that's where we need to play a little bit. That's where the remotely control is also important. We can have the sensor, we can wake the sensor up, and then we can make some preparation and we can use it. So these are the ways of coping with the fact that, as you said, receptors today maybe are not as stable as they should be. I don't know if you want to comment or to take all over.
What you said is fine, actually. We went up from having the sample die in 3 days, basically, to having the sample stored at room temperature for 6 months or 9 months, I don't remember. So that's already decent.
And last question, you recycle your biosensor as soon as the reaction occurs.
Mm-hmm.
And does it affect the efficiency and the sensitivity of your biosensor?
So that it's I guess a double tier question. One is on the sensor on the substrate and surface chemistry side, and one is on the receptor side. I think the receptor has to be stable enough, and you have to find the right regeneration compounds. And I think this will also show that we can make dozens of cycles of regeneration that we're using. I think this is definitely possible. On the chemistry side, I think we now are at the point where it's relatively stable, so this is no more an issue. But I think on the receptor side, it's still something that we need to look at. I think it's going to be also dependent on the receptor and dependent on the mutants that we can generate. Yeah. Good questions. Yeah.
Okay, thank you. Yes, please, madam.
I really like the alpha system, it's really interesting, but how do you control the non-specific binding? It's in the water, so you don't know what's there all the time, so how are you controlling for that?
Yeah. So I think if you look at the sample preparation unit, of course, because we use an SP column, then we can already isolate what is really, let's say, what is pertinent, which are, like, for example, all the toxins or the pollutants. And then with the receptor, we have the specificity there. And I think it's clear that the surface chemistry on which the receptors are bound to has some, let's say, PEG units and other things that prevent the non-specific binding. So this is a very good, that's one part. The other part is that we have reference channels, so we can look at the same water going for a reference on the same chip with the same antibody and seeing whether there's a, so it's a differential measurement so that we can get away from the non-specific binding. But this is an issue, this is clear. One possibility would be to, once we have an alarm, to actually remove the chip and take it to a micromass spec or let's say mass spec or another identification method. That would be another possibility to, let's say, make sure that the outcome is really the right one.
Okay, good. Thank you very much. So now we are